A fundamental part of a surge model is the transient event. This event is the cause of the flow rate or velocity change, which results in pressure waves throughout a piping system. In this video, we will discuss how to set up these transient events: a pump shutdown, a pump trip, and a pump startup. For more information about data input for pumps, see the videos Modeling Standard or Table Pumps in KY Pipe and Surge, and Modeling File Type Pumps for use with a pump trip analysis. First, let me explain the difference between a pump shutdown and a pump trip in the model. A pump shutdown is when the modeler turns off the pump in a specified amount of time. This graph shows the speed ratio of a pump versus time. The pump starts at a speed ratio equals 1 or at 100% normal operating speed and then ramps down to 0 or closed in 4 seconds. A pump shutdown can be rapid, just a few seconds, or it can be long and controlled, such as over 25 seconds. A pump trip, on the other hand, uses the pump inertia, torque, speed, and underlying Suter diagram to determine the rate of change of the speed when a pump loses power. When modeling a pump trip, a file pump is used where the speed in RPM is specified, so the pump speed plot is in RPM versus time. The pump starts at the specified RPM of 1200 and runs down from there. The duration and speed change rate for a pump trip is not specified by the modeler. It is instead calculated by the software. A pump startup, like a pump shutdown, occurs over a time specified by the modeler. A table pump is best suited for pump shutdown and startup operations. A table pump has an input called a speed ratio. When speed ratio equals 1, the pump is operating under normal speed as defined by the pump curve input into the ID. When speed ratio equals 0, in the node changes table, the pump is off. To define a pump shutdown, we define changes to the speed ratio, usually ramping it down from 1 to 0. As noted, a pump shutdown happens over a duration in seconds, which is defined by the modeler. The shutdown rate is linear from speed ratio equals 1 to speed ratio equals 0, unless intermediate speed ratios are defined. To set this up, select Node Changes at the bottom of the Node Info window. In this table, specify the time, change, and the value. When modeling any type of transient event, it is recommended to allow some time to elapse, just 1 or 2 seconds is enough, before initiating the transient event. This allows you to clearly see the results for the steady state condition in the graphs and tables before the transient event begins. To that end, at time 2 seconds, we will input a speed ratio equals 1. Enter 2 seconds, select pump speed, and enter a value of 1. This defines the beginning of our pump shutdown. Let's say we want the pump to shut down in 4 seconds. The next input is at time equals 6 seconds, 4 seconds after our initial input. Select speed ratio and enter 0, meaning the pump is fully stopped at this time. If we run the analysis with this 4-second shutdown, we can observe the pressure change in the pump graph, and we can see the speed ratio change as we defined it in the node changes table. Next, we'll look at a pump trip. A pump trip may only be simulated with a file or a file table type pump. Again, see the video Modeling File Type Pumps for use with a pump trip analysis for information on file pump input data. To model a pump trip, open the Node Changes table and simply select the Trip option. Do this a second or two into the simulation, same as for a pump shutdown, as shown. This analysis has already been run, and we can look at the pressure results and pump speed. Here are pressure results, and here is pump speed. As mentioned, the speed change and the time the pump takes to run down are calculated by the software, taking into account the inertia of the pump, the initial pump speed, and the pseudodiagram applied to the pump. A pump trip can be specified with a ratchet, which will prevent reverse rotation. A pump with a ratchet will not allow the impeller to rotate in the opposite direction. This model has a pump with no check valve. Following the pump trip, flow reverses, and we can see this in the graph for the pump. Here's the initial flow rate, drops down to 0 and into the negative range. Flow is reversing in this pump. The pump speed goes from 1000 RPM down to 0 and continues backwards as that pump flow reversal takes place. If we instead specify a pump trip ratchet and run the analysis again, we can look at the pump speed graph, and we see that the speed now stops at 0 instead of continuing on in a reverse direction. So even though flow is still reversing through the pump impellers do not reverse as shown in the pump speed graph. We can compare the results from the previous analysis where the ratchet was not applied. This was the pressure plot without the ratchet and the pressure plot with the ratchet. Lastly, a pump startup is modeled like a pump shutdown, but with the opposite ratios. With a pump startup, it is very important to represent the initial condition of the pump, which is that the pump is off or closed. This must be reflected in the pump data. So we'll first select the pump and turn it off. A red X appears over the pump icon. We must also set the pump speed ratio to 0. Both of these steps are required for a successful pump startup. Next, we will fill in the change data. The transient event begins at time equals 2 seconds, with the pump speed ratio equals 0, and ends sometime later, such as 5 seconds later at time 7, with a speed ratio equals 1. A pump startup defined this way is only possible with a table-type pump. A pump startup may be modeled with a file or file table pump, but special considerations are required. With a file-type pump, it is necessary to establish normal steady-state conditions at the onset of the simulation. If the pump is off at the beginning of the analysis, the operating conditions of the file-type pump will not be properly established. Therefore, it is required to begin the simulation with the pump initially running, shut down the pump, allow enough time to pass so the pressure waves diminish, then start the pump back up again. Here is a pump startup, which I previously set up, modeled with a file pump. All pumps are initially on. Pump 1 will be closed and then restarted. You can see the node changes. The speed ratio goes from 1 to 0, then some time elapses, then we have a pump startup defined with a starting point of speed ratio equals 0 at time equals 80 seconds. And some seconds later, in this case this is a 2-second pump startup, the speed ratio is changed to 1. Note the speed ratio changes plotted at the bottom. Here is our shutdown, our time for stabilization, followed by our startup. Let's run the analysis and look at pressure graph results at the pump. We want to make sure, in particular, that the transient pressures have died down considerably before initiating the startup. Viewing the pump pressure versus time plot, we can see that we have successfully achieved stabilization prior to startup. It is possible to begin a simulation with a pump at a speed other than 1 or 0. For example, you can start a pump with the pump speed ratio equals 0.9 and shut down the pump from there. But there are two important considerations when doing this. As mentioned in the pump startup discussion, a file pump should not be used in this situation unless you first start the file pump at a speed ratio equals 1, ramp it down to 0.9, or whatever speed you are beginning at, let it stabilize, Then complete the pump shutdown or pump trip. The second consideration is that if you use a table pump and start at a speed other than 1, and here we have a table pump loaded, I will start my speed at 0.9. The initial speed setting in the node changes table must match the speed ratio setting in the node info window. So if the speed is 0.9, then the first speed change in the node changes table must also be 0.9.